Hi, so in this module, we are going to continue our discussion of subprograms, and we're going to talk about how subprograms are actually implemented under the hood. And in order to do that, we have to bring in a little bit of the notion of an environment, which is a way of referring to the system on which a program is run. So every program runs in the context of a system. This includes the instructions that are available, registers, memory, I/O ports, everything from the hardware up to the operating system that the program is running with, and any shared libraries that the program depends on. And so when you have a compiler that's submitting code, for instance, you need to make sure that this code is going to be compatible with the rest of the system. So you have to obey all the rules of the hardware and the operating system. And if your program depends on any shared libraries, you need to make sure that you're using the same rules. So basically what this means is that over the years, we've created a lot of conventions about how memory is going to be used and about how all these different pieces have to work together in order to make sure that programs don't crash when you use different pieces together. And so this week we're going to focus on how we use the stack in order to implement subprogram calls. There are also conventions about how heap memory is used, but for this week we're going to focus on the stack. So I'll remind you about a subprogram. So subprogram characteristics are generally that there is a single entry point. The caller of a subprogram generally is suspended while the subprogram is executing. When the subprogram is done, control returns to the caller. And while this is all happening, information about both the caller and the callee, they're both subprograms, information about both of them is stored on the stack. And the way this works is that every subprogram that is running has a little region of the stack that is called its activation record. And this contains information about that active running function, such as the local variables to that function, any parameters that were passed to that function, any saved registers for that function, a dynamic link which points to the beginning or an anchor point in the previous activation record on the stack, and then of course a return address which tells the callee where to return control to when it's done. So both the caller and the callee have to agree about how they're going to use the stack for this purpose. And so these agreements or these rules are often referred to as linkage contracts or calling conventions. And so there are things that have to happen at the call site. This includes saving the caller status, computing and storing parameters, saving the return address, and transferring the control to the callee. There are also things that need to happen once the callee is done and we need to return back to the caller. So we need to save the return value and any out parameters. We have to restore the status of the caller, and then we have to actually control transfer back to or transfer control back to the caller. And again, here the point is that the caller and the callee must agree on these rules, otherwise everything breaks. So I find it helpful to think about this in terms of 4 events that happen and 4 different regions of code. These are things that are not in your textbook for 430, but they are in the compiler's textbook that I use. And I find it helpful to think about this. So uh, when you have a function call, so here's the caller executing and it makes a call to the callee. So the first thing that happens is that the caller executes some sort of pre-call sequence, which sets up the call. As part of that, it also transfers control to the callee, where the prologue executes, which is sort of the first part of the callee, which sets up its activation record. The callee then executes, and at the end runs the epilogue, which kind of undoes the work that was done in the prologue to tear down the activation record. And then the control is transferred back to the caller, where the post-return sequence cleans things up that may have been set up by the caller. So basically, the epilogue cleans up after the prologue, the post-return cleans up after the pre-call. So again, if this is helpful, then that's great. If not, this is not terminology that is in your textbook, so I won't expect you to know it. One thing to note here is that every function has a prologue and an epilogue, and that's because every function or every subprogram needs to create and tear down its portion of the stack frame.